Well, I'm delighted to be back here. John, thank you for such a warm welcome. Happy to be back at the museum. Software is the invisible thread, and hardware is the loom on which we weave the fabric of computing. Software, in a way, is a very fragile thing, the most fragile of things, perhaps, because a single bit and the facade that you've created will fall apart. And yet, at the same time, it is perhaps the most elegant of materials, because from it I can weave tapestries that are beautiful, elegant, that move us. Software is perhaps the most durable of materials. It can literally move virtual as well as real mountains. It can move markets, and perhaps even more impressively, it can move the hearts and minds of individuals. And yet at the same time, software can also be a millstone around the neck of an organization or an individual, because it will accumulate over time, ossifying potentially that organization and making it difficult to move forward. Software has no mass, but it does have weight in a sense. Software is also perhaps the most creative of mediums. As with a blank page, I can write anything. I can write the works of Shakespeare, I could write 50 Shades of Grey, I could write haiku. If you're really creative, you take that page and you make it fly. And that's the wonderful things about software, that it can reach many dimensions. Today I want to take you on a journey of software, because I've grown up in the software space. When I began, we had assembly language and punch cards. And now here I am today with literally outsourcing my brain to my pocket, putting it in my smartphone. And so there's been an amazing journey over those decades. And I want to walk through that journey with you from the perspective of an anthropologist. Now imagine for a moment you're a social anthropologist, you're not a geek, but you're stepping into Silicon Valley, and what would you see? An anthropologist is going to study the rituals, the ceremonies, the narratives, the belief systems of a particular community, and we're going to take that same journey. Now, if I were to do this in software, I could be here for multiple days, but I'm going to pick a couple of those. We're going to follow that journey looking at the narratives of the kinds of software people have built and the processes whereby people have built them. We could also examine this from the perspective of languages, from the perspective of individuals who have made a difference. We could also take a look at it from the perspective of the tools we use to build these things. Save that for another lecture, but we'll take those two particular threads. So imagine yourself as an anthropologist, and I plunk you down into the offices of Tumblr, and here's what you see. Well, putting my mindset on as the anthropologist, I look around and say, what curious individuals these are. I might watch them for several days, and I would see them come in the morning at various strange hours, and eventually they'd all stand up and talk for a while, and then they'd go back to their respective devices and toil away, and it would look like a very, very boring kind of activity. There would be curious symbols around, this little smiley face. I'm not sure how that advances my software development, but it's there. We'd also see a variety of tools. Different people are using different kinds of monitors and the like. Now, there's something really interesting here that I wonder if you'll point out. We'll give you an experiment. As a cultural anthropologist, look here and tell me one of the things that really stands out. Do you see it? Yes. Where do they hide the women? Where do they hide the women? And it's true, sadly so, in this particular culture, and I'm not condemning Tumblr, it just happened to be this one particular page, one particular picture. There are no women in this picture, and yet, as we will see, women played a seminal role in the evolution of what we know today as software. Now earlier I spoke about what software is as a material. It's very, very fragile, like silk itself. It's very durable, like granite. It is very fungible, as it is with writing. Let's take a look at what software development is like. For some, developing software is like building a doghouse. You just take whatever's in front of you, you build it, and you do it. We sometimes call this agile programming. If you fail, you can always build a new doghouse. If you really fail, you can always buy a new dog. Sometimes software development is like building a house, especially if it's your own house, because now all of a sudden I've got some skin in the game. I'm building something that I've got to live in, literally eating my own dog food here, and so the risk is higher, the cost is higher, and I'm going to do a little bit more planning because of that different risk perspective. So it's kind of like building a house, and in a way, it's never done. You get to a point of closure where you finally live into it, you get a certificate of occupancy, but ultimately, even once you're inside there, something always needs to be fixed. A lot of software, frankly, is like managing a city. Imagine yourself inside Paris and realizing what I'd really like to do is put this Hyperloop straight through the middle of the city. Wouldn't that be nice to do? Problem is, you piss off a lot of Parisians who are in the middle of that Hyperloop. And so the reality is that you have many stakeholders in a situation like this, and you can't always make the change. Now you could do, as has been done in China and other places, you just say, heck with it, I'm just going to build a new city. Poof, there it is. And that works sometimes, but by and large, cities that have economic value and human value tend to grow organically. In fact, many of those cities in China are veritable ghost towns. So what you really want to do is to take a place like this, like a Paris, and slowly evolve it over time, and such is the nature of large software-intensive systems. Developing software is also like raising a child. You make up stuff as you go along. There are lots of people telling you how you should be doing it. And the hardest problem probably is learning to let go. Old software doesn't die, you have to kill it, by the way. Developing software is like building a movie, producing a movie. You'll get together with some of your best friends and say, let's go do a movie. And you throw them together and you have this frenzy of activity and you build something and you release it. And if it's successful, you're allowed to build a sequel. If you're really successful, you have a whole franchise. But there are a few franchises, and we all migrate to them, but there's still a lot of other software out there that entertains us, and movies that entertains us and delights us and fills some space in our world. Developing software is a lot like sex, and you'll notice I don't have a picture. We'll leave this to your imagination. It's a lot like sex because it's both an art and there are mechanics associated with it. Furthermore, you get better with practice. And to paraphrase Richard Feynman, sex, like software development, like research, sometimes it produces good results, but that's not always why we do it. So let's go back in time. I mentioned in the picture of Tumblr, there were no women present. But actually, as David Greer in his wonderful book has observed, the first computers were women. This is the time, here we are in 1890. These are the Harvard computers, the women who actually computed. So we have your first, this is a classic stand-up scrum. So now there's some are standing around, they're all talking to one another. There's a manager who's not doing anything over to the side. Classic agile development. And what we have here is the beginnings of the art and the science of software development. The Harvard computers in this time were mostly women because it was not deemed to be an activity that was worthy of the time of men. Can't believe that. And what they would primarily do would be to take raw data from the astronomers and then do raw calculations upon them. So we began to see the notion that this munging of information was best done in small teams of really bright people. As we move forward, we began to see some automation come into play. And here we see kind of an assembly line, the very idea of the factories of software development come into play. Now keep in mind, as we think of the shape of software in this time frame, we're still largely dealing with purely numeric systems. We're just munching numbers in various algorithms. But it was clearly discovered that there is indeed a factory that we can build here. We put in raw data at one end, each person does a little bit of computation, passes it on to the other, and we finally end up with something at the end. Very menial, very mechanical, but indeed it was valuable. It produced some good results. And so we begin to see the ideas of some degrees of formalism coming into the process. Now, there were alternate models. Move ourselves to the 1930s. We see Vannevar Bush working on a differential analyzer, and it's also a pipeline kind of thing. We set up this system, and we're going to come back to this when we talk about quantum computing toward the end. We basically set up this machine, we turn it on and let it do its thing, and we get some results. It's kind of like how quantum computing is today. But again, it's the idea of a handful of people working around a machine to get some results. Move ourselves to the 1940s, and now we see a really fundamental shift. There was a classic book written in this time frame by J. Presper Eckert. I forget the exact title. I think it's Punch Card Methods in Scientific Computing. That's the title. Great book. Go read it if you're really bored some night. But he begins to outline the patterns that we have discovered in that time frame for how to take a scientific problem and begin to decompose it into its pieces. So again, we see another element of the puzzle come into play, the idea of decomposing a larger system into its component pieces. No women in this picture, by the way, but we see here a legion of men who, again, as in the previous two pictures, would work kind of in this pipeline. You'd take some data in, you'd operate upon it in one way with this machine, pass it on to the next. As we move now to the late 40s, then there was another discovery, another realization. If you look closely, the dapper young woman off to the right side, that is Grace Murray Hopper. And she, of course, was working on this machine and was perhaps the first to realize that there was something other than the machine itself with which we could begin to work. Still in this time frame, we're largely dealing with numeric systems. We're largely dealing with the activities of software development, really wasn't called software then, as one of controlling the machine. The distinction between hardware and software did not yet exist. Now, if we move to the bowels of Bletchley Park, go read Sue Black's book, by the way. Delightful book on basically how she saved Bletchley Park. Wonderful, wonderful book. And truly she did through her efforts. But here we have one of the rare pictures that came from Colossus. I told the story in my first lecture here on Woven on the Loom of Sorrow, dealing with computing and warfare. But to recap a little bit of it, remember that the Colossus was born out of the work from Tommy Flowers, the engineer, who took the ideas from Turing and others, from the Tunny. Go watch The Imitation Game and you'll see some pieces of it. Great movie, by the way. Great acting, compelling plot, terrible history, but it's fun. It looked like, Turing saved the war. He did do some fundamental things, but it's people like Tommy Flowers who actually built the Colossus and designed it that made it real. But what you saw in the Colossus was the discovery that we could indeed introduce ideas of loops and conditionals and run something against it using the ideas from Boole and Shannon. I think Shannon was around this time, which said it's possible to actually build a machine that does algorithmic things. And that was the tremendous breakthrough that we saw with Colossus. You would see in the little tape here, that's where an encrypted message would be put in, constantly running through, and then we'd finally, in a way, find a relaxation algorithm off to the side here that would discover the potential settings of the Enigma and Lorenz machines' keys or rotors. But again, still, the fundamental problem was numeric, a little bit symbolic, but also the distinction between software and hardware was simply not there. We had people operating machinery. I think the true beginnings of programming happened with the women who programmed the ENIAC. There's a delightful website and a children's book and a small documentary called Top Secret Rosies, which tells this story a bit. I urge you to go take a look at it. We also talked about this in Woven on the Loom of Sorrow. But again, here was the task. You would have some men off to the side that would say, we want to do this calculation, and quite literally they would toss it over to the wall to this set of women who would try to figure out, how do I arrange the plug boards to do those calculations? So again, the first computation was still largely numeric. It was largely done still on the hardware itself, and it was done by this team of really bright women who simply got together and figured out, how do I do this? In a way, you can begin to see some of the beginning seeds of what today we call agile methods. You would have clear demonstrable results on a regular basis. You would see a small team working together with sort of a maniacal focus. But nonetheless, we were still dealing with just managing the machine. Now, from this point on, we can see a bit of a parallel path here. We're going to look at the story of software from two ways. I'm going to look at it from the people and the processes, and we're going to look at it from the growth of software itself as a thing. And along the way, I want to share with you what I perceive as the major epochs of software. But here we are in the, let's put ourselves in the 50s for right now. And it was only in this time frame that the term software became a legitimate term. In fact, the first time it was used appears to be in either 58 or 56, depending upon which source you take a look at. And the first use of software was not as the stuff that runs on a machine, but the stuff that was not hardware, mainly people. So they were talking about methods associated with the personnel involved with the system. It only came a little bit later that when we began to realize there was stuff that runs on the hardware that could be named unto itself. So for right now, as we begin this part of the journey, we're dealing with the problem is, how do I manipulate a machine? How do I command a machine to get results? There's no software, it's just managing the machine. Then, of course, came along John von Neumann, who had the brilliant realization, and of course working with Eckert and Mauchly and the like, who realized this notion of a stored program computer changes the equation. What if, he said, we take the ideas of controlling the machine and actually put it inside the machine itself? This is one of the brilliant, strange loops that software itself embodies. I use a phrase here that comes from Hofstadter in his delightful book, Gödel, Bach. And it reflects back to what I showed you earlier about taking the piece of paper and turning it into an airplane. One of the beautiful, elegant things that moves me in software is the presence of these kinds of strange loops where we turn software unto itself. And here's the first example of that, where we turn our machines into themselves, realizing that our machines can be controlled by programs within the machines. If you look at the problems that von Neumann was attending to, they're very interesting ones, because his first problems involved how do I model the forces around a nuclear weapon, because it was a little bit messy to try to blow these up all the time. So let's model them. He was also looking at weather forecasting. He was also looking at artificial life, things that we are still struggling with today. So the roots of the problems that we faced back in the 50s still exist with us. We're still trying to move the ball forward in each one of those. I think it was in this time frame, with the presence of the Joniac and all that von Neumann was doing, was the beginnings of understanding in the marketplace that there was this other thing out here and it was worthy of discipline unto itself. So we saw the beginnings of hardware having this little bitty layer of software on top of it, and we began to actually call it software in that space. Still, most of the software was still in assembly language. We saw a little bit of higher order languages, but largely it was to control the machinery in ways that solved some problems. The shape of our problems were relatively small. We're dealing with applications that might be hundreds, if not maybe 1,000 or two lines of what we would call code today, and most of it was still numeric in nature, although we began to see the shift toward symbolic kind of computation. In fact, scientific work came a lot out of being woven out of the loom of sorrow from warfare. It was business that drew us to the symbolic side of things. We began to realize that these characters could represent not just numbers or tallies in a warehouse, but they could represent people. And so all of a sudden there was this second shift in our understanding of software, that we had the notion that software could mean something. There could be some semantics to it beyond just the underlying mathematics. So you see here a phase in which we had this curious combination of punch card technology as well as more modern technology. There's a hard drive off to the side here, which probably by comparison sakes is far less than what I'm carrying in my pocket right now. But we begin to see the discipline that there was indeed a set of people who could do the software versus could do the hardware. And thus began the programming priesthood. And what I mean by that is, quite literally, you would have a set of programmers over here who would devise their solutions. They'd have little cards or little forms in which they'd write out their cards. They'd carry them over to be key punched. If you're dealing with a large organization, the key punchers would take that, hand you your deck of cards. You'd carry that deck of cards, hopefully not tripping as you go there. You would walk up to the machine room. You would hand it to the person there behind the glass wall, genuflecting as you go. And you'd walk away. These people would go behind the wall, behind the curtain, do their magic, and then come back to you and say, "Yea, verily, my son, you have a syntax error," or you have... But we began to see this dichotomy, a growth of the software space and a growth of the hardware space, but a separation between the two. And the reason for this is the economics of the situation were very interesting because machines were more expensive than the humans. And therefore, it was important for us to optimize the use of the machines. We would queue up the humans so that we could, keep feeding things into the hardware monster to keep them as busy as we can, because these were darn expensive devices and those humans were disposable. But the separation began. So again, we see a little bit more layer of software coming into play. This is around the time where we saw the notion that sharing ideas of software was a good thing. The first ideas of open source came to be with IBM Share, literally an organization meant to share algorithms, share code with one another, so we wouldn't have to keep doing it again. From the hardware-software perspective, the other shift we saw is we began to move away from these machines that were behind these glass walls, and all of a sudden, we could put devices on them that people from outside could begin to talk to them. And also not just humans, we found ways that we could take those machines and have instruments that are in the world begin to communicate with them. And so the equation for how we were using the machines was different again. So again, we moved from numeric on the cusp of symbolic, and slowly but surely, we were moving these machines out of their glass cathedrals and into the world. A great example of that is Sage, which is perhaps in its time the largest software development project there was. We spent billions upon billions of dollars. And it was through the Sage activity that I think we learned two things. Software is really hard. And second, there are some processes that work and some that don't. In the Sage era, there was a tremendous amount of software built because all of a sudden we had these great machines, and now we realize that their fungibility, their power came from the ability to separate the hardware from the software. So we began to see this wonderful path of the two diverging. And software unto itself had economic value. And it had value in the sense of the ability to not just control our machines, but to adapt our machines. It was from the Sage experience that we also learned that there is this software crisis going on, that the cost of building software was increasingly a limiting factor in being able to deliver systems of value. And thus we saw, this is later in the 60s, when we had the NATO report come out on software engineering that declared the presence of a crisis. And its impetus was a lot of what was coming out of defense systems. In fact, it is fair to say, the premise we made in Woven on the Loom of Sorrow, that much of what we knew about software engineering and hardware came out of the World War II and the Cold War. The largest systems that anybody built were coming out of defense systems. And in the case of the Sage in particular, there was a lot of software. And this is an interesting system too, because it was never used in anger. We never really used the full capacity of the Sage system, but it was a system that made us feel good about having. It really did. We spent billions of dollars on a system that we never used in anger, but its presence gave us something to defend against what the Soviet Union was doing at the time. And of course, the Soviet Union was progressing forward in a way that made what was happening in Sage utterly obsolete. So that's the defense side of the world. Let's jump forward to the business side of the world. Today, we have the Googles, Twitters, Facebooks of the world. They're the dominant forces that you may see in the marketplace. Move yourself back to the 60s, it was IBM, and it was the 360 all over the place. Again, it was economic factors that were beginning to drive the software equation. The 360 itself existed because IBM wanted to preserve the software investment their customers had made and be able to upsell them across machinery. And they viewed it as an opportunity to do hardware sales. But the unbundling of software from hardware and the creation of an architecture that allowed the preservation of the software itself represented a fundamental shift in the industry, because now all of a sudden software had real economic weight associated with it. And this is where the notions of structured methods came into play. Because here, the fundamental problem facing us is, like in the defense world, all of a sudden we were building larger and larger systems. And the methods we used for simple systems just didn't scale up. So what do? Well, this is where waterfall methods came to be. Because if it works for building a warship, if it works for ordering 10 million staples, then by God, it's got to work for software, right? That was kind of the way of thinking. And believe me, I was in the midst of this time frame as well, a little bit later time frame, but the notion of waterfall methods still applied because it makes a lot of sense. You analyze your requirements, you design everything up front, and then you start building things because, again, the cost of these machines was still so high. It made sense to push the thinking process earlier on in the process, because changing it later on was very, very expensive. So the 360 changed the economics of things, but it also changed the software side of things, because all of a sudden we had more software and yet more software. And thus we had the crisis. Another woman onto the scene, Margaret Hamilton. Here we are in the 60s. Margaret is standing by a printout from some of the Apollo 11 guidance control software. In fact, go over in the exhibits, and I think we've got one of the Apollo 11 guidance computers sitting there. This is the software behind it. There's some debate on this matter. There are some that say it was the NATO conference in 68, 69, that declared the term software engineering. And it was intended to be a provocative term, because we're talking about engineering this soft stuff. There's reason to believe that it was Margaret that actually used that term before anybody else. Apparently she had used it in some of her internal writings at NASA, and NASA, go back to the NASA archives and you'll see this, and it appears to have predated the NATO stuff. So I'm going to go to the benefit of the doubt, and I think it's Margaret that coined this term. But the point of her term was that she saw that the very process of building software was an engineering process. Now, what does that mean? Put your mindset on of an engineer and realize that this largely means building systems that optimally push back against the forces upon that system. So if you look at software from an engineering point of view, you look at the stakeholders on you, you look at the forces on you, quality, performance, functionality, reliability, security, all the usual illities, changeability as well. And then you ask yourself, how can I build a system that reasonably weighs against those? Because as we know in engineering systems, there is no such thing as a perfect system. There's just a good enough system. What you began to see in this time frame too is the evolution of true formal software methods. This is where the structured analysis methods came to be. So some of the greats of Tom DeMarco and Ed Jordan and Larry Constantine, Harlan Mills, and those are from sort of the production side. On the academic side, we have Edgar Dijkstra, Parnas, Wirth, C.A.R. Hoare, Mary Shaw and others, who are beginning the notion of a theory of computation and a theory of software development and a theory of architecture. Not quite there yet, but we were getting there. So at least what Margaret began to realize and brought to the marketplace is that, and certainly we saw this in Knuth's work, there is an art and there is a science, there is a mechanics to what we're doing in software itself as a legitimate activity. So our software and hardware systems began to grow and grow. Our devices became larger. Our devices became smaller because of the revolution of the microprocessor. Now all of a sudden, the equation changed for us as well. We used to have these huge machines that were more expensive than the humans, and now all of a sudden we were moving to machines that were about on parity to a human. And now I could make my machines personal. I could literally spend the time to go in and me as an individual work and manipulate one machine. We also saw the software problem beginning to grow, and thus the growth of a variety of languages. So we saw, in conjunction with both methods and languages, these two things growing up. In the previous eras, we had the algorithmic languages, Fortran, COBOL, C to a degree. And now we began to see languages that were a little bit different. They were languages like Simula that started to come onto the scene. SPSS was around this time frame. Languages that helped us solve problems that were very difficult for us to express directly to the computer. So the shift here that was happening in the mindset was the discovery of the power of abstraction. The entire history of software engineering, I would declare as one of a history of abstraction. We moved from the numeric to the symbolic, and now in this age, we were starting to build, as David Klertner would speak of it as, mirror worlds. We were starting to use our machines to build worlds unto themselves, and now all of a sudden our software was not just numeric, was not just managing symbols, but it was actually creating our own worlds. It was creating worlds into which we could step, and the mini-computers helped us do that. Another curious thing happened as we began to shrink our machinery is that the things on the edge of our devices could start to have intelligence within them as well. So no longer were these stupid devices, but now the programming problem had shifted from being in the data center to being out on the edges. Another theme we're going to see that's been repeated today, this move back and forth, the pendulum swinging back and forth between centralization and decentralization, because thus was born the PC in its various forms. Now, this also changes the software equation, because now all of a sudden we had the notion of the predecessor to the app. I could build a standalone thing that could make a difference. Thus we see the creation of, for example, VisiCalc, which really made the marketplace for the PCs in the business world, built by a couple of guys, and it changed the world, this piece of software. All of a sudden now, you had a change in economics, because a small set of people could now go off and write some software independently from a set of hardware that other people supplied. And there was economic value in that. So we saw, continuing on, the structured methods and the like, but by and large, our applications were still islands. They were monolithic things you would control from the top of the end, and you controlled everything around it. You controlled the entire ecosystem, and that worked reasonably well. This is the time frame of the operating system wars, because what happened is we discovered that in addition to the software, it made a lot of sense, rather than writing against individual hardware, let's settle upon one or two different operating systems that give us that layer of abstraction. Again, the growth of abstraction. So now, this is why we saw the operating system wars in this time frame. People were debating over whether or not, is it Windows, is it Unix, is it whatever Apple was trying to do here, is this the right platform upon which to build? And economics was very much changing and pushing and driving the software marketplace. We don't have those wars anymore, because, quite frankly, operating systems are down in the noise for us. We're building things on top of them. We'll come back to that. But down in this time frame here, we're still largely building islands on top of one another, until, of course, ARPA came along and said, what happens if we tie these things together? What happens if we take these devices that have intelligence and allow them to communicate? So all of a sudden, our software problem shifted again. No longer were we building things for one machine, there were islands, but now all of a sudden we were building things that were in an ecosystem of lots of other peers. And the question then is, how do we architect things? How do we deliver things that can leverage that value of interconnectivity? We saw our networks grow and grow until we sort of have them today. There was another shift, because now all of a sudden it wasn't just these devices that never moved that were on the edge, but now some of them were mobile. How did that change the software equation? All of a sudden, we were now no longer building applications for a single machine. We were building it for the context of multiple machines. We were also building it for devices that were on the edge, that had their whole intelligence, that leveraged those things on the edge. Clearly, we were discovering that what we knew from the 60s and 70s in terms of how to develop software just wasn't working for us. And so it was around this time that you saw more of the language wars coming into play. This is, jumping ahead of this particular time frame, We saw this is why we had the creation of the Ada programming language. The DoD realized there were too many languages around. We needed to reduce those to a small number. So is there a way we can take modern software engineering techniques and put them in a language? Again, a realization that language really does make a difference. Well, consider the other languages that were popping up around that time. We had Simula, we had Bjarne working on with a thing called C with classes, which morphed into C++. There was Smalltalk around this time frame. We saw a generation of languages that was very different. And it grew from this shift in problems that we saw from numeric to symbolic to mirror worlds, because now we were building languages that allowed us to build simulations. Very much what Simula was all about, and it led us into the object-oriented paradigm, which of course Ada tried to adopt. Very quickly we realized that the techniques of structured methods, from Jordan, DeMarco, Constantine, all these kind of folks, just didn't work because they were the wrong abstraction. And thus was born object-oriented design, object-oriented analysis, and I and my colleagues were deeply in the midst of that. And that also led us to discover something new about the way software was developed. That rather than having these big monolithic phases where I do analysis, design, implementation, and deliver it over the wall, the industry was beginning to discover the ideas of continuous evolution. The idea that there should be a punctuated equilibrium, that rather than waiting to the end, where things tend to break, let's try to incrementally get milestones along the way and bring these things together. Such was the nature of software development in its nascent state in the 80s and 90s timeframe. But here's the other shift that began to happen. As we saw these devices, and from here to here, this is sort of the ARPANET as we saw it way back when, with devices that were in glass rooms. All of a sudden we started seeing devices that were outside of the centers. But then we also started seeing some of those devices that had intelligence unto themselves, and some of those devices that were very, very personal indeed, and that were talking to things in the world. Thus was born the beginnings of the Internet of Things. Because all of a sudden we began to see that we could take ourselves out, move our devices from where they were behind the walls, and put them firmly into the world. This also changed the nature of software development, because now we were fundamentally dealing with systems that had to deal with the realities of the real world, and the real world is very, very messy indeed. There's another economic change that happened, and that was the creation of the cloud. Why did the cloud come to be? Pure economics. We see this enormous cost in our data centers, and we realize there is tremendous commonality. Wouldn't it make sense, therefore, to begin to consolidate those ideas and get the patterns we have of each of these one-off data centers and put them into the clouds themselves? And thus we have Microsoft, we have IBM, we have Amazon, all building these cloud kind of things. And that also changes the economics of software development, because now all of a sudden I can build something that fits across virtual machines that could literally be anywhere in the world. And I have a different problem to deal with now. In building islands, I didn't really have to worry about security so much, but now I do, and it becomes an important engineering factor that did not exist before. Prior to this time frame, I could build systems whose access I could trust because I actually had the key that allowed people into those machine rooms. Here, the world is different. As David Deutsch once also observed, you can define a distributed system as one in which the failure of a system you didn't even know existed can cause your system to fail. That's the true nature of a distributed system. And so we were now building systems that were living in a fragile ecosystem. In fact, speaking of ecosystems, the shift we began to see was also another economic one. There's this idea of dominant design, which says that in any discipline, you're going to find a number of players that begin to go into the marketplace. And after a while, you will see consolidation around a particular set of them. And so this is what the ecosystems are all about. We see an ecosystem around Amazon. We see an ecosystem around Google and Facebook and Twitter. We see ecosystems in other places as well too that are industry specific. So we're beginning to see the creation of these lines drawn that are economically driven by a small set of companies. That also changes the software development perspective, because within those ecosystems, the shift that has been happening is taking those raw monolithic systems and componentizing them. What we did in Watson is exactly that strategy. So when we won the Jeopardy challenge and we had taken Watson out of the laboratories and put it into the world, teaching it how to look at MRIs and X-rays to detect cancer, dealing with all sorts of things in that regard, we realized that one of the things we could do with the Watson platform is to refactor it. And so we took it and refactored it into some 27 different services. In the decade past, we had the operating system wars. Now we have the microservice wars, in which people are less worried about operating system because that's just a design choice by and large. But now the real engineering choice is, what set of services do I build myself on? And we're finding that the companies who build these ecosystems are the ones who have economic value in dealing with them. You may have some that are lost leaders that say, we'll just give you all these services, but because you're using them, we get all your data, yahaha, and we can monetize it. There are others who are trying to monetize the service themselves, but again, the focus is not on the operating system wars, but upon the service wars, who controls the services into a particular ecosystem. And that's the componentization that's happening. Now, that's where we are today. And that's where you see sort of as a snapshot of software development. So let's take inventory of what we've got. We tend to still build really large systems. By and large, these ecosystems are on the order of tens of millions, if not many more lines of code. If you read some of the works coming out of Google, they will tell you that some 50% of their code bases or their files are touched I think they said every month or every quarter, some very small number. That's a whole lot of code. And so there is a set of people within these ecosystems whose sole responsibility is to keep feeding the beast, much like we used to do with the operating systems, keep adding services, keep building that infrastructure, keep drawing people in. There's a lot of software development happening in that space. Another place where the software development is taking place is especially what you see in the Valley that's VC funded, which says, let's take those services. I can't afford to build them my own, but by God, let's build a company on top of it that begins to use those services. And so rather than building things of my own, the infrastructures of my own, I'll go off and get some time on a cloud, I'll get a bunch of smart people together, and we're doing things on the edge. So what's happened is that software development, by and large, has broken itself up into three spaces. We see development that's happening behind the services, where a lot of C and C++ and now Java tends to go. You see a lot of stuff on the outside of the services, where a lot of JavaScript and scripting languages tend to go. And that's what most of the press talks about because it's cool and it's sexy and everybody uses Google and Facebook and Twitter. But there's a third piece that nobody ever talks about, and that's the stuff that lives in the walls. That's the stuff that lives in the devices in this room. I'm looking right now and I see a whole bunch of devices up here, and I gotta believe there's a few million lines of code in some of the stuff that I'm seeing. Go to any rock concert and you're probably gonna see a set of lights that are run by a company called Verilight, which has a fantastic operating system behind it, originally built on the Macintosh platform. Lots of lines of code. So there's a third set of software development going out there that's largely in the hard real-time, near real-time space, and they don't get nearly the amount of press that's going on. But by and large, we've moved from numeric to symbolic to mirror worlds, and each of these places is a world unto itself. Let's project forward a little bit. Where is this headed? Software is becoming incredibly intimate because now no longer are these devices just out in the world, they are inside us. They are becoming attached to us. And the economics indeed changes again. If I do a Google search, or if I'm writing the code for some algorithm for Facebook to bring up feeds, please bring up, if any of you Facebookers are out there, please bring up a regular timeline feed for me, please, please, please. Stop all this algorithm shit. But now we're dealing with a set of people who are building systems that touch us intimately. And if I fail to build up the right feed in one of those cases, nobody's probably going to notice. If I miss a bit in my heart, in my pacemaker, somebody's going to die. So we're dealing with very, very different economics in this space. So we're beginning to see, as I move forward here, we're deeply in the midst of the Internet of Things. That's great. But what's happening is that intelligence is now moving out to the edge. We're seeing the move from what we could do more so in our data centers out to the edge themselves for two reasons. The first has to do with the sheer ability that we can. We now have the algorithms, we now have the sensors, the battery power, et cetera, that allows us to put more computational resources out to the edges of our system. But the other reason for it goes back to the physics of data. That if I have a wind turbine, or if I have a turbine on a jet on my aircraft, I actually can't afford to take all the data that's being generated there and put it back to my data center. If I'm out there on the Orion spacecraft and I've got a problem, I can't report back to mission control because there's a 30-minute delay due to speed of light. Therefore, I need to bring mission control with me. This is the HAL problem, by the way. Truly is. I think we know how to build a HAL, albeit a less dangerous killing type one. But the economics, the physics of data say that moving that amount of data is incredibly expensive, and therefore it behooves us to push computation out to the edge. So the shift we're beginning to see is greater intelligence out to the edge. In fact, earlier I mentioned that the first computers were human. Well, what's happening is that we're moving in the direction of the current computers are human. There are 3 humans and 3 non-humans on this. The non-humans are sitting here. And if you look at the work David Hanson and others have done, we're leaping across the uncanny valley. We absolutely are. If you look at the direction that Microsoft is headed with their bots, we've seen a lot of work in that space, great stuff. What's happening is that we are now moving our software systems away from our hardware and back to the most natural form of communication we had, which is like me talking to you. It's conversation. But it's not just my voice, it's also my body language. I'm pointing to people, I'm nodding, I'm winking, and it is therefore through force of action as well as force of influence that I am interacting with you. Now, this leads us to neural networks. We know today that the most efficient way to build a functioning neural network requires the activity of 2 unskilled individuals, a waiting period of 9 months, and then crowdsourced education. This is the proven way to build a neural network. So I absolutely celebrate what Google has done with DeepMind and AlphaGo and the like. Great stuff. But remember that there are some things that neural networks can't do. I can't go to AlphaGo and ask the question, why did you make this move? I can as a human because I've got many more millions upon millions of neural networks. What we know how to do with convolutional neural networks today, we don't quite have the capacity. So here's the shift we are seeing. We've been moving from systems that are largely deterministic to systems that we teach and that learn. And that changes the life cycle altogether. It used to be the case in my software development process, ads or not, I'd build something, I'd have things I could test against it, I could incrementally build something up. In fact, the Googles, Facebooks, et cetera of the world, anybody who has these ecosystems have built really profoundly wonderful lifecycle tools that manage the build, release, delivery process. There's a high degree of automation that goes on there that makes it possible for individuals to make changes on a daily basis to these kinds of things. We've achieved that degree of automation in the infrastructure, but not in those other 2 domains that I spoke of. We've still got a ways to go. But what's changing now is now I'm introducing neural networks, now I'm introducing quantum systems, now I'm introducing cognitive systems that are not necessarily built on neural networks that I have to teach and that learn. And so this changes the development life cycle because now all of a sudden I've got this component. Maybe it's an NLC or NLP kind of component, or maybe it's some vision recognition thing, and I've got to train the classifier, and I put it into my system. The problem is then, where do I do that in the life cycle? Because the very presence of that thing changes the delivery of what I'm doing. And furthermore, the training continues to happen after the delivery of that system. We saw that with the Microsoft bot that was released upon the world that was saying nasty things. It's just like a child. You teach them the best you can, but you put them out in the world, and by God, they do some strange things. So it is with our software. So let's go back to first principles then. That's the present problem, and that's the problem you all face. or will certainly face, and certainly your children will face, how do I build software systems that I teach and that learn over time? How does it change the life cycle? There's one thing I can say about software development in general that transcends every one of the things I described. There appears to be three overlapping phases of stuff that goes on. There's a period of discovery, there's a period of invention, and there's a period of execution. And these three things overlap. In our waterfall methods, what you would see is these were non-overlapping. In our agile methods, we make them very much overlapping. And where I think we're headed with our learning systems is, I don't know. This is why I need you to come up with the answer. But what I do know also is an idea that comes from Herbert Simon that applies here as well. We Agilists speak of the notion of continuous integration. It's not a new idea because it comes from nature. We speak of it as punctuated equilibrium. This is what Herbert Simon spoke of in the great book, The Sciences of the Artificial. And he observed that all complex systems tend to have stable intermediate forms. And so let me offer the following to you. No matter what kind of software you're developing, no matter what it is, there are really some fundamental principles that apply no matter what. Focus upon good abstractions, have a clear separation of concerns, and have this set of punctuated equilibrium. Have delivery of demonstrable things over time. Everything else is details. It truly is. But these appear to be the meta rules that cover the art and the science of software itself. Now, each of you are in a different place in software. And one of the things that's hard for me to explain to people who are not in the software space is that there are many different flavors of software. You know, the bane of our existence is you go up to somebody, random person, and you tell them, oh, I'm into computers, and they'll say, oh, can you fix my smartphone for me? Well, yeah, sure, but that's not exactly what I do, but I'll help them anyway. I'm sure it's happened to all of you. So here's a mental model you might use when you try to explain to people what it means when you do software. There are three axes you can consider. Now remember the three I talked of. We talked about below the services, on top of the services, and outside in sort of the Internet of Things space. Here's another decomposition. The first is the degree of formality associated with it. Like the doghouse, like the house, like the city, there are different amounts of stakeholders involved, and therefore it is reasonable to consider different amounts of formality. If I'm just building a doghouse for myself, yes, sometimes I'm in the doghouse, then I just do it, and there's no formality. But if I'm changing a city, there's formality. Another way is to consider the risk. If I do this and it fails in some way and nobody cares, so what? But on the other hand, if I accidentally launch a global thermonuclear strike, this is generally known as a bad idea. And so I have higher risk, and therefore that changes the kind of software I build and how I build it. And the last is one of scale. That I love having these debates with Agilists. Kent Beck and I have had some delightful conversations in this space in terms of the role of architecture. And the reality is that as you move to larger and larger things, I'll flat out say Agile methods don't scale up. You've got to do some other things. When you're starting to deal with hundreds of thousands, if not a million lines of code, or millions of lines of code, you've got to approach it differently. The great thing about being a software developer is this. This is thinking back to the page we saw earlier. The basic premise of science says that we can look at the world, observe it, and we can reduce it to a set of understandable fundamental principles. This is what the standard model is all about. The premise of our domain is that the cosmos is computable. We can take a small set of things we know about the world, the notion of computability, and we can build anything. We can deal with numeric things, we can deal with symbolic things, we can deal with our own kinds of worlds. We, as software developers, are in a fundamentally different space. And what this history has shown us is that the history of software development is just as fascinating as the history of hardware. Walk these halls and go to the exhibits and look at it next time from the eyes of the lens of what software was running here. Because the stories of software are as vibrant and as full of avarice and delight and serendipity as they are with the hardware. Let me leave you with this. At the beginning, I said that software is the invisible thread and hardware is the loom on which we weave the fabric of computing, I'm going to frame it in a different way. Software is the hidden writing, and it whispers the stories of possibility to our hardware. Software is the hidden writing that whispers the stories of possibility to our hardware. And here's the exciting thing. We're the storytellers. We are the ones who are in a place where we can tell those new stories. We have the opportunity, we have the privilege, we have the responsibility to tell the stories that change the world. What an exciting place to be. Thank you all very much. Cool. You guys get some good code written back there? Get some good code? You probably wrote a bit of code and released it, and it's out in the world already, right? Let's talk.
Nice. Thank you.
That was fun.
It was fun. You see what I mean about him sitting at the intersection of the humanities and technology? That's an English major thought that you left us with there, in addition to all your prowess in software. So thanks for coming back. You guys did a great job. I've got some amazing questions here, far more than I can, I'm sure, get ready to answer in the time available.
You know, be willing to do?
But let's try.
Leave those questions with me, and I may blog them or tweet them or email something. So.
Okay, we'll do. That's a great idea. First, what technologies do you use to build Watson, and why?
Let's see. Watson was built, well, let's see. How do I describe that? It's mostly written in Java. There are bits of other scripting language here and there, but by and large, it's Java that runs it from top to bottom. We used Eclipse as most of the primary IDE that people tended to use. And we built a lot of our own tools. The problem I mentioned of teaching of systems that learn traditional methods and tools don't work, we found that to be true. So we had to build a whole set of tools that would enable us to look inside a reasoning system and be able to ask, why did it reason a certain way? So I think we had a whole team that was going off and building those. The other thing I'd mention process-wise, it was a classic Agile project. David Ferrucci, who led it, had a war room where the 30 or so people would get together. They'd see their little scoreboard that they'd look at every day. We built a build and release process that would allow us to test against JArchive on a daily basis, so we could come in the next morning and see what worked and what didn't. Classic Agile activity. And also, there's another great book I should mention by Jim Copleen called Organizational Patterns of Agile Development, in which he looks at some of the patterns for what works and what doesn't. David followed that as well too. You've got this thinker off to the side, which is David. And you've got a couple of architects, and you've got the people that orbit them, and that's exactly how we structured it.
Okay. How many lines of code in Watson can you estimate?
The Watson Jeopardy one was pushing around 10 million lines of code. If you add all the pieces we have now, it's easily doubled or tripled those pieces right now.
Amazing.
And also, I should add, we also have neural network stuff in it, and I don't know how you count lines of code there. You can count numbers of neurons, but that's not a very satisfying number.
You clearly got some attention with your comments on quantum computing, so let me ask a couple. Will software have to, quote, start over, unquote, in an era of quantum computing?
Great question. So I'm happy to report that I work in an organization, IBM, that actually has a lot of quantum computing scientists in it. And as I interact with them, they tell me the following. It reminds me a lot of what Vannevar Bush had to deal with. You've got this difference engine, you set it up, you turn it on, and you get results. That's a lot of what quantum computing is today. You basically set your qubits up, you put them in a certain configuration, you wait for your result as it calculates in multiple dimensions, and you get back. There is some work going on to identify languages for quantum computing, but they're completely non-von Neumann. Ditto with artificial neural networks. In the ANN space, we're using an ecosystem called Caffe, which is not so much a language, but is more sort of a development system. And basically, the situation is you define a convolutional neural network, you shake it in certain ways and look at it again, you shake it again, and that's the development process around it. But there aren't many languages for us. So in the quantum case, nobody seems to know. Nobody really knows. But I will observe that for at least the foreseeable future, a lot of what's happening in quantum computing is still pretty much compartmentalized. We see it doing certain computationally complex things, but not the symbolic or mirror world things like we see here. That's not going to happen anytime soon.
When we get really smart people on stage, we often get a question like this, and I'm always so happy when it happens. What are good topics for computer science students to study that would be valuable in the next 10 years?
Wow. That's a really good question.
It's a really good question, isn't it?
So I'm going to answer that in two ways. The first is, make sure you get a good grounding in things that are outside your comfort zone, that force yourself to go look outside your current sphere and go read things that are totally wild and crazy. And I mean even out of the computer sciences. Go read Herbert Simon's book, And the Sciences of the Artificial. Go read Hofstadter. Go get yourself inspired by different ways of thinking. And I also say in general, go look at the problems of computational thinking. Can you sort of refactor your brain and start thinking in different ways by looking at some of the stuff that Jeanette Wing and others has done? The last thing I'd say is, do something outside your comfort zone. Go build some crazy piece of software that makes you happy and learn from it.
Yeah.
Try something different.
Yeah.
I mean, that's why Jan and I are doing this crazy documentary. It's changing up my brain.
Yeah.
And I write books and I do these kinds of things because I want to learn. And that's why I'm doing them.
Oh, that's good. How do you envision the future of AI? You talked about it a bit. I think we're going to drill down here and say, will it eventually be smart enough to replace human workers, including software engineers? This is a question that probably is of importance to a lot of people in this room.
You say that as if it's a bad thing. Actually, we've got an effort that's looking at that. I've seen several people that are asking the question, what can we do to apply AI to the problem of software development itself? The low-hanging fruit deals with testing, that we see already some fruitful cases of using AI agents to help us in the testing process. So that's a good thing. The process of design, well, I've already seen some activities where people are looking at AI agents that can sort of sit in my pocket and nudge me saying, hey, have you considered using this pattern? Or hey, have you looked at this software over here because it looks awfully similar to that? That's where I think AI is going to move into the problem of software development itself.
If the two camps are human augmentation, human replacement, let's just as a sweeping generalization,
Sure.
Where do you think we're headed down that fork?
Well, I don't think it's a fork.
Ah, okay.
Because I believe human augmentation leads us to human replacement. As I think I gave a lecture on this once on the notion of the computability of the mind, and I have the premise that the mind is computable. My lovely wife disagrees, but that's okay. She's wrong. But
you take a lot of that abuse.
You take a lot of that abuse. Remember the doghouse thing I was talking about?
Yeah,
earlier?
no wonder you're in the doghouse.
I'm going to be building a doghouse later today.
Yes, you are.
So no, we have some great discussions. So I'm of the mind of Rodney Brooks, who views that there will be no singularity, because by the time the singularity comes, we ourselves will become robots. So I think already I outsource my brain to my pocket and my smartphone. Already we see the beginnings of neural implants. I've got an Oculus Rift on order, and I'm jazzed about that kind of thing. I'm actually working on some things in elder care, so literally I'm working with a team that's building software that I hope will keep me alive when I'm in my hundreds and tens. So I'm building software to keep me alive. So all these things represent the path of human augmentation. But at the same time, you have to ask yourself, are we in fact building things that lead to a new species? And if I want to go really far out, I'd say we probably are. That I see this symbiosis, this dance between computing and humanity, thus the name of our documentary, that I think there is that weaving together that may lead us to that new species. And I don't view that as a bad thing. I view that as a natural part of evolution.
You seem to imply, this question says, that the operating system wars are over because what's now happening is we're building microservices on top of operating systems. Please explain further, if this is what you think, why there is no need for a better operating system today.
Well, let me tease that question apart. It used to be that the choice of an operating system was a technical choice. It is now an economic choice, not a technical one, because I have to make the decisions about, do I have the right trained people? Does it work on the right platforms? So the decision process has changed. There was always room for something better, and that's why I celebrate people building new operating systems, new languages, but the problem is one of economics. That I see people working on new programming languages in particular, and I really celebrate what they're doing, but the chances of that programming language ever making a difference in the world is approaching zero, unless you're an Apple and you have people who built things like Swift, that you can have this immediate platform on which you can do it. But if you're off in the corner somewhere and you're building a language or an operating system that still is a better mousetrap, the problem is people have beat their paths to another doorstep already. So again, it's not a technical win. Very rarely, once in a time, you're going to see a language or an operating system that will win on technical expertise, but it's the economics of software that are driving it now.
There were several questions here. I was just sorting them again about your concept of the other. And this question asks, how do video games reflect on your view of this concept of the other?
Well, I'm a Halo player myself. I love video games. I'm desperately waiting for my Oculus Rift to come to move into that particular world. I mentioned the notion of the move from numeric to symbolic to mirror worlds, and video games are one great example of that because we create worlds unto ourselves in those spaces. And if you look at the evolution of software in video games, I've had some delightful times to sit down with the people at Electronic Arts, and there was a few years ago where I kept seeing them build these one-offs, and I said, why doesn't anybody go off and build a game engine that you use over and over again? And the economics were such that it finally did shift in that direction. So what you began to see in the gaming marketplace is a consolidation around a set of gaming engines around which people could build narratives. So the same thing that happened in the outside software world happened inside the video game world as well.
One final question. Tell us about software in 50 years. There's a smiley face on that card. So.
Well, for those of you writing software in the back, the people up in the front will be debugging it 50 years from now. Probably. Software for 50 years from now. I'm going to answer that question from the perspective of shape of software, process, and language. From the perspective of language 50 years from now, we'll probably have some new languages, but still there's going to be a lot of Java and C++ around, and Swift around. I hope somebody will have invented some new languages, but the reality is, like the Granite example at the beginning of my lecture, software lives on and on and on. It's amazing to realize, I think I used this analogy once, there is software that the IRS uses today that was written in the 50s and 60s that's an assembly language, and we still have it today. So software you write today is still going to persist in 50 years from now. So we'll see some new languages, but there's still going to be a lot of old stuff. I think in terms of processes, we're going to probably do better at automating the process, like what we've seen the Googles, the Facebooks, the Amazons, the Apples do for those circumstances that are reasonably well understood, and we're doing lots and lots of iteration. There's a great opportunity for automation in that regard, and I think we'll see that move out. As for the types of software, I think we're going to build more and more software that really leverages the distribution that we have, even beyond what we have today, and also leverages the kind of interfaces that we can only dream about, the augmented reality and the virtual reality things, and the conversational things we have here. So that's the shape of the software we have to build. And that means there's still a whole lot of software to be written. The parting thing I would say is no matter what future you might imagine, it relies upon software that no one's built yet. So there's a lot of fun stuff to do.
I'm going to give you the balance of these cards. Please. You can answer and elaborate.
I will. Thank you.
Just want to say that it's brilliant that we could have Grady here today because the entire Computer History Museum is pivoting towards software. In fact, it's one of the two major areas of expansion for us. We're about $18 million into a $30 million fundraising campaign that will launch, among other things, a Center for Software History. And the last remaining space on the ground floor that isn't open to the public is now under construction. And on January 12th, 2017, if you happen to be a forward planner, you're invited to come see the opening of a new exhibition called Make Software Change the World, which is going to be about 8,000 square feet. It's going to be the most interactive thing we've ever done. We're going to iterate on it as the years go by, just as software iterates on itself, and it will really be a kind of new era for the museum, and you're helping lead that entire initiative. So thank you very much, Grady, for being the influence that you are.
Thank you. Thanks for having me.
Have a great day, everyone.
Thank you all.